everybody doing?
Good. How about you?
Everything is great. We're coming to the close of the general management comment period, so that'll be nice. Have that over, then I know what I'm going to do for the next month. Analyze comments. We'll see how that goes. So we have a little treat in store for us today. We have somebody here who likes to study old things. and it's great because today's my birthday. And so, and then tomorrow's Park's birthday. Tomorrow's Park's birthday, so we can talk not as old as what you're going to talk about. But we have Dr. Dan Muhs with us, and we've built quite the professional relationship with Dan. But I think what's even more important is the friend relationship with Dan. He's fallen in love with this park, and it's so funny that every time we end up having a conversation, he's working where I've worked before. And so that's been kind of funny. He spent a lot of time in Alaska. But I think what's important for you to know is that Dan is not only a geologist, he's a geomorphologist. So he likes to know how all the geology moves around. But what I think is even more exciting about it is he's what I call a charismatic geologist. So I didn't study geology because I figured I had my whole life to study geology. Nothing, there's nothing exciting about it until you talk to people like Dan, and then you find out, wow, he can make geology come alive, and we do appreciate that about you. And in fact, that's why Dan is also doing a guide to the geology of the Channel Islands, because just think how exciting it would be to have somebody like him who can make it all come alive, and that people would really understand the substrate in which all this biology sits on top of. So it'd be really exciting. So with that, Dan, thanks for coming through the weather, because he is stationed in Denver. So we had to come through some weather to get here, and luckily we cleared all of our weather off the table for him. That's a little nicer, and I understand you're going to the islands tomorrow, right? So he's not just here to talk to us, he's also here to do some more work on the geology of the Channel Islands. So with that, Dan, thanks for coming, and we can't wait to hear the talk today.
Thank you. Well, thank you very much. Well, that's an awful lot to live up to, but I'll do my best. So thank you very much for all your kind comments. I should mention it's actually the 135th anniversary of the US Geological survey as well, where I work. So we actually got a message from our director saying happy birthday to the USGS yesterday, and her monkey message. So lots of birthdays. Anyway, thanks so much for inviting me to come here. Yvonne Menard kind of organized this for me, and happy to be here. Always fun to talk about stuff that we found. And so I'll give you a little discussion about one of the charismatic fossil characters of the Channel Islands, which is the Pygmy Mammoth. So we'll talk about that a little bit today, and some new things we've learned about that. Maybe one thing, is it possible that these lights could go down just a smidgen or all the way? I'm going to quickly go line. And I think the slides will show up better too. That's great. Perfect. Is that okay? Yeah. Very good. All right, excellent. Okay, so I'll talk a little bit today about the sea level history, the uplift rates, and the antiquity of the Pygmy Mammoth, or in its Linnaean terms, Muhs exilus on the Channel Islands. And this was a big team effort, as most of our efforts are these days. And so my collaborators are here. Most of them are USGS folks, but there's also, I'm going to have you turn off all the lights. Okay. Lindsay Groves with the LA County Museum, who has identified all our fossils out on the islands and who's never been here, but we're going to take him there tomorrow, and his wife as well. Steve DeVogel at the University of Colorado, and Larry Hagenbrod, who's Mr. Channel Islands Mammoth, as you know. That's maybe the one light we really don't want. That's okay. I figured out where the button is, so you can go down to, there we go. Okay. And now that I said that again. Okay. What I would like to do is dedicate this also to one individual in particular who had a big influence on my life. And this is a guy named Don Johnson. Here he is with his wife Diana in the summer of 1969 up at the head of Niagara Canyon on San Miguel Island. And Don taught at the University of Illinois, but did his PhD work, his dissertation research on San Miguel Island in the 60s. And he was a big influence on my life in terms of not only heading towards the earth sciences, towards geology and geography and soil science, but he introduced me specifically to the Channel Islands. Although I grew up around here and kept seeing them, because we would take a drive from little Lompoc to Santa Barbara or someplace like that. We'd always see the islands. I was always fascinated by them, but I'd never visited them until Don and Diana took me there in 1976. Sadly, Don passed away this last spring, just a little less than a year ago, and we lost a great Channel Islands researcher, a very great friend, and just a heck of a nice guy. One of the nicest guys I've ever met, and a great mentor for me on the Channel Islands. So, Don, this is for you. And as you'll see, Don's research and thinking will enter into this talk quite a bit as we get on forward. And a big thank you to Channel Islands National Park. This is the best national park in the country, and it is my favorite place in the world. And it's a wonderful place to work, and everybody here at Channel Islands National Park has been nothing but wonderful, start to finish, on everything we do here. So thanks again to Channel Islands National Park for all your support. So we're going to talk a little bit about the mammoth, and specifically the Pygmy Mammoth on the Channel Islands. But I want to set the stage a little bit by talking just a little about the broader picture within North America of where the mammoth fits in. And the mammoth, like a lot of other the big megafauna or big animals, is one of the more iconic, classic sort of ice age animals of the last glacial period, which was from about 30,000 to about 10,000 years ago. And here in North America, and I should add there were mammoths in Eurasia as well, but here in North America there were two that were the most common and widespread: the Columbian mammoth, or Mammuthus columbi. And these are all the sites that have been compiled where it has been found. And you can see it was primarily in the western and central United States, and a small separate kind of population here in Florida, and one oddball up there in Pennsylvania, it looks like. And then also the woolly mammoth, or Mammuthus primigenius, which was a more northern species, and you can see it occurs more in the northern states here and up into Canada and Alaska. There aren't a lot of sites within Canada, primarily because this was covered by a big ice sheet at the time of the last glacial. There probably would have been plenty of sites up there without that ice sheet. The woolly mammoth actually immigrated from Asia through Alaska here, but the Columbian mammoth actually evolved here in North America. And I'll give you some lineage here that will explain that in a bit. And as almost everyone or everyone in this room knows, mammoth remains have been found at a number of locations on 3 of the northern Channel Islands. Haven't found anything on Anacapa yet, and haven't found anything on the southern islands yet, except for one tooth on San Nicolas Island, which was probably transported there by prehistoric peoples, we think, as a ceremonial object. That's the explanation in archaeology. When you can't explain an artifact, it's a ceremonial object. But here we go. On the northern Channel Islands, we have them on western Santa Cruz Island, quite a number of sites on Santa Rosa Island, and then a number of sites on San Miguel Island as well. And these are sites that have been compiled to a great extent by Larry Agenbrod in Cushing, and also Don Johnson in his studies on the Channel Islands. And then a recent find of ours that is one of those red dots up there. So, and this is what I'll show you a sequence of what some of the typical mammoth finds have looked like. This is by far and away the most famous one. This mammoth right here, with Bill Faulkner here as scale. Oh, I'm sorry, other way around. Anyway, this one, which was the most complete mammoth skeleton ever found, found by Tom Rockwell at San Diego State. and excavated by Larry Agenbrod and Don Morris and their whole crew. And it's been radiocarbon dated by Tom Stafford at around 15,000 years, which puts it into the last glacial period. Beautiful specimen here, and a remarkable find, and quite a rare one. And I'm sure all of you have seen the display that's just over here that replicates that. More commonly, what we find is the kind of thing that Luis is pointing to here, which is just a single tusk. And here it is blown up over here. This is at the mouth of Water Canyon in a bunch of alluvium or stream deposits that you can see here. And you can see from the size of the boulders that this is kind of like the floods that hit Boulder, Colorado, where I lived last September. And you wonder how a tusk like this could even have survived such a transport, but it did. And so what you're looking at is a tusk there that is sometimes the kind of thing that you find on the islands as well, and certainly much more typical than a complete skeleton. On San Miguel Island, we have the Johnson family again, pointing to, there we go. This is Diana Johnson, or part of her anyway, pointing to some mammoth remains at a place called Running Springs on western San Miguel Island. And this is Don Johnson pointing to a tusk fragment at Running Springs. Don also found a piece of cypress charcoal from here. Got a radiocarbon date on that of about 18,900 or so. By the way, this nomenclature, you see cal years BP, that's calibrated years before present. So radiocarbon years are different from calendar years, and so we actually have to calibrate them a little bit. They're sometimes not off by very much, and sometimes off by as much as about 4,000 or 5,000 years. During this time period, the radiocarbon date on this would have been about 15,000 years. But you'll see this term cal years BP. You can think of it as calibrated years BP, or it's easy to remember, think of it as calendar years BP, as opposed to radiocarbon years. Anyway, there's Don pointing to the tusk that was with charcoal associated with it. It's dated to about this time period. Again, that's in the last glacial period. So, where did these guys come from, these pygmy mammoths that we see on the Channel Islands at outcrops like at Running Springs and Water Canyon and over on the Carrington Pony area where that nearly whole skeleton was found? Mammoths actually kind of evolved from Asian immigrants. The primordial immigrant, if you want to call it that, to North America from Asia was Mammuthus meridionalis, this guy here, big-sized mammoth, as you can see from the scale, maybe as much as 4 meters tall or so. We don't know exactly when this guy arrived to North America from Eurasia, but probably somewhere between 1 and 2 million years ago or so. So it's been around for quite a while. It's been extinct for some time as well. We don't know exactly how long it's been extinct, but it did not coexist with the pygmy mammoths that we see here. But it did spawn a new species here in North America, the Colombian mammoth that I showed a picture of before. And that guy in turn was the ancestor of the pygmy mammoth. So the Mammuthus meridionalis immigrated from Eurasia. After getting here, some of them were ancestors of Mammuthus columbi, and that in turn spawned Mammuthus exilis, or the pygmy mammoth, here on the Channel Islands. And just to show these two guys next to each other, you can see the pygmy nature of the pygmy mammoth compared to the Colombian mammoth, typically about 4 meters tall for the Colombian mammoth and just under 2 meters tall for the pygmy mammoth. This is based on a lot of the skeletal analyses that Larry Agenbrod has done with all of the finds that have been made over the years. Okay, so how did they get here? And this has always been an interesting question, and it's really interesting because it was literally the better part of a century before there was really a firm conclusion about this. And the typical explanation had been land bridges, that somehow the Channel Islands had been connected to the mainland and that they walked out here and then were isolated, and that was it. They stayed out there until they became extinct. The problem is there was never any geologic evidence for a land bridge. None whatsoever. No geophysical evidence, no geologic evidence, and interestingly, no other biologic evidence as well. And the main piece of evidence along those lines, sorry about this, thing just went crazy on me. Don Johnson, the very guy that I was describing earlier, showed that there was not only no geologic evidence, but if there had been land bridges, we should see other mammals on the islands, but we don't. Why are no other large mammals that we find in the fossil record of the Channel Islands if there was a land bridge that they could walk out across on? Why would only mammoths have done that? There's absolutely no reason why there would. And yet this was the idea held in the literature, scientific literature on this, for nearly a century, was the idea that there had to be land bridges. So these are some of the reconstructions that were made, some of them quite imaginative, where all of the islands are connected here, or nearly all of them, Catalina even, and Santa Barbara and St. Nicholas, all connected together to the Northern Islands and on up past Point Conception, and for all I know, all the way up to the Aleutian Islands. But in any case, lots of different reconstructions, none of which there was a shred of evidence for, except the presence of mammoths on the Channel Islands. That's it. Okay, and there's other problems. If we take a look at this, the shallowest zone that we see in here is right between Ventura and eastern Santa Cruz Island. But the shallowest zone, and there is a nice flat, shallow area out here, but it's about 230 to 240 meters deep, okay, at present. And the closest distance, really, between any of the Channel Islands and the mainland is about 20 kilometers from Oxnard to eastern Anacapa Island, okay? And if you go to a more habitably or suitable island for mammoth habitat, you're looking at a distance of about 30 kilometers or so, something like that. So you're looking at significant distances here. But during the last glacial period and during prior glacial periods, didn't look like that. Because a lot of water from the oceans was locked up in glacial ice like this. Today we have some locked up in Greenland. But we had more locked up in Greenland at that time during the last glacial period, 25 to 10,000 years ago. And two big ice sheets, the Cordilleran ice sheet here in western Canada and the Laurentide ice sheet in eastern Canada and the north-central United States, a huge amount of ocean water was tied up in this moisture. And a smaller amount in the Fennoscandian ice sheet in, in Europe as well. But not as much as these two. These two were the big players. And today, all that's left of the Laurentide ice sheet is the very tiny little Barnes ice cap on Baffin Island up here. And it's getting smaller and smaller all the time. So, when you tie up this much water from the oceans, that has moved from the oceans of air masses, fallen as snow to form these glaciers, you lower sea level by a lot. And in fact, there are a couple of different estimates of this. Our estimate from tropical locations is that sea level might have been as much as 120 meters below present. We now know that there are different sorts of records on different coastlines because ice sheets, with the weight that they put on the continents and the way that the weight of the oceans on the ocean floor changes, it actually changes relative sea level from coast to coast. So depending on where you are, sea level could have been as much as 120 meters below present or as little as 95 meters below present. But either way, yeah, this is a big revelation to me too. The world's ocean is not a bathtub, okay? It actually differs from place to place because of gravitational effects and weight on the crust and all of that. But with either of these estimates, you shorten the distance from mainland land to what would have been a large single island called Santa Rosa, dubbed by Phil Orr back in the 60s, down to about 7.2 kilometers or so. A very short distance by comparison with that 20 to 30 kilometers you would have during interglacial conditions such as the present. So Santa Rosa not only was a very large island, much more suitable for animals like mammoths to live, but getting there was less of a problem. But you still had to get there. There still wasn't a land bridge. Even with a lowered sea level as much as 120 meters, remember that distance over here, or that depth over here? 230 to 240 meters deep, okay? That's a long way. You would have had to produce ice sheets that were more than twice as large as the last glacial period ice sheets. We have no evidence that that happened anywhere, okay? If that were the case, we would have seen the Laurentide ice sheet going all the way down to New Orleans. It didn't, so we know that didn't happen. But you've shortened the distance quite a bit. So what Don Johnson contributed to this was the hypothesis that elephants swam out there. And he documented this with some careful archival research and some examination of some of the abilities that modern elephants, both Indian and African elephants, have for swimming. And it's been documented most recently on Havelock Island in India, where this guy named Rajan, the famous swimming elephant of Havelock Island, is documented here. And you can see here's this guy trundling along with no problem whatsoever, uses his trunk as a snorkel, and can swim across. And Don showed that there were some absolutely incredible historic occurrences of elephant swimming events in a lot of situations. Easily a half a kilometer to a kilometer or more, and in one case 48 kilometers off the Carolina coast once, although it was a forced swim because of a ship accident. But nevertheless, they had the ability to do it. So this finally explained why we didn't have any evidence for land bridges, but we did have elephants or mammoths out on the Channel Islands because they're good swimmers, and they swam out to the islands during glacial periods when that distance was minimized between mainland and the islands. So if we put this in the context of glacial interglacial cycles, this is a kind of complicated looking curve, but it's not as bad as it looks. And I'll try to walk you through it. This yellow line you can think of as a sea level curve. Okay? It's actually an oxygen isotope record from deep sea cores all over the world, but it is basically mimicking glacial interglacial cycles and sea level fluctuations. So the present interglacial is right there, and over on this axis are ages in thousands of years. Okay, so 100,000 years, 200,000 years, and so on. And you can see glacial interglacial cycles are about 100,000 years long, and all of these red letters or numbers here, which are odd numbers, 11, 9, 7, 5, 3, 1, are oxygen isotope stages, as they're called by the deep sea community, and those correspond to interglacials. The ones in blue, for cold, are our glacial periods, and you can see those are the even numbers going back. So here we're going back about 450,000 years. We have a whole series of interglacials, like the present one, and glacials, like the last one. Okay? So it was during the last glacial period, about 10 to 25,000 years ago, that sea level was at its lowest, somewhere between 95 and 120 meters below sea level, when that distance was shortened. Mainland to island, Santa Rosa was created, and we had only 7 kilometers that the elephants, or the mammoths in this case, had to swim to get over to the islands. Okay? So there we are in that period. If that's true, then we should see evidence of much of our dating of mammoths to the last glacial period, right? And so we'll look at this period of time in a little bit more detail. What we're going to do is just take this portion of the curve and we're going to stretch it out, I think, like this, okay? So here we're looking at stage 1, our present interglacial, stage 2, the last glacial, stage 4, the glacial before that, and the last interglacial, which is a complex of high sea stands here. So high sea level, a little bit lower, 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 low, a little bit higher, low, and then up to the present sea level. And here's all the mammoth radiocarbon ages that Larry Agenbrod has compiled. And sure enough, look where most of them fall, is right in the middle of stage 2, or the last glacial period, with a handful of them maybe at around 30,000 years, but still during a period of time when sea level was a little bit, quite a bit lower than present. And that also would have been a time when sea level was low enough that mammoths could have swum out. Okay? So the model fits together fairly well. That from the fossil record that we're seeing and the dating that's been done on it, and what Don Johnson's suggestion was about when mammoths should occur out on the Channel Islands during the last glacial period. Okay, Don also mentioned that, well, okay, if that's true, this is in the same paper, possibly this scenario occurred several times during the late Pleistocene, those are the ice ages, resulting in a population of elephants on Santa Rosa with different degrees of dwarfness that at times may have existed contemporaneously. This is something he hypothesized in 1978. And it turns out, I think he's exactly right. And Larry Agenbrod also pointed out that because the Columbian mammoth was the ancestor of the Pygmy mammoth, we should see both of them out there on the island at the same time. And the fossil record that we have, and the dating that's been done indicates that's true. But most all the dates are to the last glacial period. Don was suggesting that anytime you had an ice age, this could have occurred. Okay? No reason why the last glacial period was anything particularly special. There were previous glacial periods that were just as intense, where sea level would have lowered just as much. Mammoths, we know, have been in North America 1 to 2 million years. Why not earlier ones? Okay, this intriguing idea then is what we're going to take a look at. And here's the last glacial period again. We've stretched the curve out again now to 450,000 years again. So you can see we've got stage 10 here, about 350,000 years ago. Stage 8 at about 250,000 years ago. Stage 6 about 150,000 years ago. All these glacial periods where sea level is low and would have been times that mammoths could have swum out to the islands as well. Did they? That's the question. So, where do we look for something like that? We want to look at something we can date. We want to look at something that's widespread on the islands. We want to look at something that could preserve these things as well. One of the best records we have on this on the Channel Islands are marine terrace deposits. And marine terraces are things that look like this. This is near Point Fermin in the San Pedro area, not too far from the lighthouse there. If you're familiar with that area in LA County. This is a wave-cut bench at low tide that's been exposed. This is what the waves have cut in the surf zone, where they've cut the bedrock down, planed it down due to wave action and organisms that live in the tide pools that burrow into the rocks that loosen it up and weaken it. And as this expands during its formation, the sea cliff retreats. Okay? And so we get this nice sharp junction between a sea cliff and a wave-cut bench that we call a shoreline angle, which is this junction right here, and is very close to mean sea level. Okay? So that's a baby marine terrace or an embryo marine terrace. And then when a place experiences uplift, most of coastal California does slowly over time, this gets lifted up out of the way, and that's then called a marine terrace. And so if we look at it schematically, this is this wave-cut bench forming in the surf zone. Sea cliff is retreating. And then when we get a glacial period, sea level lowers, this thing is left up high and dry, and then uplift over time lifts it up out of the way. And then when the next glacial period or interglacial period comes and sea level rises, it starts cutting a new one. So as a result of that, what we end up with is a sequence like this. This is the same sea level curve that I showed before, although I've scrunched it down here, but back about 450,000 years. So each one of these high stands of sea is represented on the landscape by a marine terrace. The one in the surf zone being cut now, and then the last interglacial leaves this one. Last interglacial before that leaves this one, and so on. And we have a series of kind of stair-step landscapes that look like this. And if we look at the landscapes of the Channel Islands, we see exactly this kind of pattern. This is one of the most obvious ones, which is on San Clemente Island. And here you see a series of wave-cut terraces that form during each one of the interglacials of the last, in this case, 500 to 600,000 years. The last one coming right here. Okay. We see them on the northern islands as well. Here's San Miguel Island, an old U.S. Navy photo that Don Johnson gave me. Here's the last interglacial marine terrace with these red arrows pointing to it. And then there's a higher terrace right up here. That's the outer edge of it. And then it kind of gets buried by all of the sand dunes that have developed over this part of the island during the course of its history. And then this flat tableland over here in the western part of the island is this same terrace again over here as it pops out underneath the sand dunes. And we see it even on the littlest islands. Here on Santa Barbara Island, we actually have 4 of them. Square mile. Very small island, and we have 4 interglacials recorded here. Here's the last interglacial marine terrace. There's one up here around 50 meters that the Park Service building is located on, and the campground as well. And there's a couple of higher ones as well. And Santa Rosa Island, which we're going to zero in on here, has got loads of them. Most of the island is a marine terrace landscape around the northern, western, and southwestern parts of the island, and a little bit on the southeast as well. There could be marine terraces even in through here, but they'd be so old that a lot of them have been eroded away. We've identified 3 broad groups: young, older, oldest. Kind of like, I had to come up with some sort of Starbucks terminology for that no one understands, like venti, whatever, marine terrace. But I'll resist that temptation. At any rate, we've got lots of them here on Santa Rosa Island, and we've been studying these for the last few years. Here's a picture of what some of them look like in the Betchers Bay area. Here's the last interglacial one. It's about 120,000 years old. An older one here, still older one here. And on the southern part of the island at Johnson's Lee, they're all over the place. Here's the last interglacial terrace here. There's another one up here, higher one up here, possibly a higher one here, possibly a higher one up here, and so on. So if you look closely, you start to see marine terraces everywhere, and they're all over the place. And it's really a big part of coastal California's landscape because of the continuing uplift that most of coastal California experiences. Interestingly, where to look then within the marine terrace record on the Channel Islands for old mammoth possibilities was actually given to us by Phil Orr in 1960. And he's talking about the lowest marine terrace on the north coast around Garanon Canyon. And he talks about the marine facies. Facies is a term for the type of sediment family in a sequence of sediment families that occur. And he's talking about the marine sediment, if you want to call it that, in that area on the lowest marine terrace, a light gray calcareous clay, blah, 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 containing fossil bones of whales, sea lions, sea otters, shorebirds, and occasional dwarf mammoth, okay? As well as organic remains and quantities of rotten asphalt, blah, blah, blah. And then also a marine fauna, and here he's talking about mostly mollusks, okay? That becomes important for dating these, as you'll see here in a minute. But this was one of the clues. He found dwarf mammoths in 1960 in these marine terrace deposits and speculated, even way back then, that mammoths could have been out on the Channel Islands prior to the last glacial period. Okay? Remarkable insight due to just careful field work. So we went out to this area since we were studying the marine terraces there as well and looked. This is the general area. There's Garanon Canyon, where Orr did a lot of his work, and where we have found some very, very rich marine records as well. So this whole landscape that you're seeing is a marine terrace that's mantled with dune sand and stream deposits and so on, but it still retains that flat terrace-like landscape shape. And then we have older marine terraces on the skyline here that are this, form these sort of concordant summits about the same elevation all along there. But the deposits are beautifully exposed in Garanon Canyon and down at the mouth of it as well. And if we look in Garanon Canyon, near the mouth of it, very closely, we can actually see that there are 2 marine terraces in here. Here's the outer edge of the second one. This is bedrock, the Rincon Formation, which is a shale. And this is stream deposits that have been laid down on top of it. So this is the old wave-cut bench. And sure enough, when you look on top of there, you can find fossils, marine fossils, loads of them. And then this is the old sea cliff going down to the next lowest and younger marine terrace. And its wave-cut bench is traced all along there with that yellow line. And then these are stream deposits that have buried it. Okay? Still retains that marine terrace look because the alluvium kind of covers up and smooths over the whole landscape, but follows that original marine terrace topography. All right? Now, what's interesting is that right out here, there's a little sea stack, which is a chunk of rock offshore that is part of the mainland, but is a little more resistant. So it sticks up as an erosional kind of remnant. It used to be once connected to the mainland, or island, whatever the case may be, that is now stuck out by itself. That's called a sea stack. Well, it turns out a lot of this marine terrace stratigraphy is still preserved out in that little sea stack, despite all the best efforts of the Pacific Ocean to get rid of it. Okay? So we looked there, as well as all through that canyon, and guess what we found right in there? Here, I'll just walk you through it though first. This is the Rincon Shale. There's the wave-cut bench. There's a series of marine boulders that have marine fossils in them, and then alluvial deposits or stream deposits on top of that are still left over. And then right on top of the wave-cut bench on that Rincon Shale, we found this. And that's a beautiful tusk that with these dimensions, Larry Agenbrod assures me, is a Pygmy Mammoth. Okay? Now, it's sitting right on top of the Rincon Shale wave-cut bench. It has marine terrace deposits that have fossils in them that occur above it. Okay? And there's whale bones in here, all kinds of other stuff. So that tusk was transported from land, probably during a sea cliff retreat episode, as the wave-cut bench was forming, eroded from the land, fell into the surf zone, was preserved there as it got buried by sediment, and then as uplift took place, left high and dry for us to find later on. Okay? So there it is. It's got to be older than the last glacial period because it's forming on a marine terrace deposit, so we know that the host sediment is of interglacial age. And unless it were from the present interglacial, it has to be from at least something as old as the last interglacial. Okay? So we knew right away this had to be an older marine deposit. Had to be a pre-glacial, pre-last glacial mammoth. So Orr was absolutely correct in his observations, and we found what he had found as well. So how do we date that thing? There's at least 4 different ways that we can date marine fossils. Not the tusk itself, those are tougher to do, but marine fossils in it have a variety of ways. Radiocarbon dating is a possibility. It's got to be less than 50,000 years old, or we're at the limit of radiocarbon dating. We can use strontium isotopes, but those have to be at least 300,000 years old, so we're out of luck there. We can do it with uranium series dating, which will take us from anywhere from 0 to 500,000 years, but we need corals for that. Now that does get to be important for what I'll show you here in a minute, because we have dated a lot of our marine terrace deposits in California with corals. There are little solitary corals that live off the California coast now. They're like their tropical cousins. They take up uranium from seawater, so we can date them that way. Okay? But in this case, we didn't have any corals with that tusk, but we did have mollusks, and we can use amino acid ratios in mollusks, and we can compare those to amino acid ratios in the same mollusks from marine terrace deposits that have been dated by uranium series methods on corals. Okay? That's called amino stratigraphy. This is kind of the leapfrogging type of geochronology that geologists do all the time, where you don't have the right material to date this, but you have something else, and you can compare it to something else that's been dated by another method. You can tie them together. That's called correlation. And it's a big concept within the geological world, and we're going to do it today. So I'll show you how. So everybody knows this, of course. Actually, you do, because this stuff is in your body right now. Amino acids are the kind of the building blocks of protein, and there are all kinds of amino acids, of course. But what's interesting is that there are different configurations of amino acids in what are called the D and L configurations, which are basically mirror images of each other. Okay? Now, as it turns out, living organisms only have the L configuration. So L-isoleucine is something that is in your body right now as part of your protein makeup. So is L-isoleucine. So is L-glutamic acid, L-aspartic acid, et cetera, et cetera, et cetera. Lots of amino acids. What's interesting is that although living organisms only have these L configurations, when an organism dies, those L configuration amino acids begin converting to their mirror images, which is the D configuration. So L-isoleucine starts converting to D-isoleucine, okay? And it's a reversible reaction. It goes back and forth until a kind of an equilibrium ratio is present in the formerly living organism, but now fossil organism, of about 1, okay? It takes time for that to occur, all right? What turns out is that fossil mollusks that we find in marine terrace deposits still preserve a lot of these amino acids in measurable amounts. And we can measure the ratio of D to L amino acids, and if we calibrate that, we can date something. So this is how it works. We measure the D to L ratio. This is age in thousands of years. Ka means kiloanno, so it's 20,000 years, 40,000 years, and so on. Glutamic acid increases its DL ratio kind of at this rate. Aspartic acid, a different amino acid, jumps up much more quickly, okay? So what that means is we can use different amino acids for different sort of time periods. If we want to get a lot of resolution in this time period, we can use aspartic acid and separate things out. If we want to go farther back in time, before we get to 1, which would be out there someplace around Anacapa Island, we could use glutamic acid, okay? But we can use these amino acids then, once they're calibrated, or where we can compare them to a dated deposit, which is a kind of a calibration, to date things just by measuring the amino acids in a very simple fossil mollusk shell. Every California marine terrace deposit has got them up and down the coast from here to Oregon. So this is the one we use, tegula, which is now known as chlorostoma. And you can see them at low tide, actually right by where we found that tusk. Here you can see them close up. Little crabs will sometimes get into these guys after they die. You'll see them wandering around. You think, my goodness, that's a fast-moving snail. And it turns out it's actually a crab inside there using this as a house. But they're very common in the rocky intertidal environment. Not so much a sandy bottom type environment, but rocky intertidal, which is good because that's what the channel islands mostly are. And we get beautiful amino acid ratios from these guys. And this is an example. So what we've done here is we've looked at the D to L ratio, in this case in glutamic acid, in tegula, in a series of marine terraces that we've dated from Punta Banda in northern Baja California to the PV Hills, San Diego. I put Point Loma before the PV Hills even though it's farther south because it's actually cooler here than it is here. This is sort of temperature increasing and going north in this direction, all the way up to San Luis Obispo County. And what you see is the DL ratio in marine terraces that are dated to 120,000 years generally decreases as you go north. And that makes sense in terms of what we understand about the reaction kinetics of those amino acids. 80,000 year terraces also decrease as you go north, but you can see that they are separated from and are clearly distinct from the field defined by these 120,000 year terraces. Okay? So if we look at another amino acid, in this case valine, this has a DL reaction that is a bit slower, so the curves shift downward, but we can see the same general trend, decrease as you go north, and a decrease as you go north in terraces dated to 2 different ages. So these are distinct from one another. So we can tell 80,000 year terraces from 120,000 year terraces. We had terraces that we dated to 200,000, they'd form a field up through here. 300,000, they'd form a field up through here. Eventually, when we get to a point where we're at about 1 for a DL ratio, it all stays the same. Okay? And it doesn't change. The reaction's going back and forth at an equal rate, and it's reached an equilibrium, and that's the end of the dating technique. Okay? Well, we can take it back about 1 million years around here, based on the temperature that we have in this area. Okay, so knowing this, we can go to a place like Santa Rosa Island on the north side, or where it's a bit warmer, Santa Rosa Island on the south side, we find mollusks like tegula, measure them in the lab, we can figure out, is that terrace 80,000 years old, 120,000 years old, or something older, or something younger. And so that's what we did. And it turns out the lowest terrace is 80,000 years old, and the one up above it in Guiranon Canyon is 120,000 years old. And this makes perfect sense because we find a lot of these 80, 120 terrace pairs all up and down the coast. At Punta Banda, in Peavey Hills, in Point Loma near San Diego, just across the channel there on San Nicolas Island, and on San Miguel Island as well. I don't have it up here, but we have found it on San Miguel as well. So this is the terrace where we found the mammoth tusk. So we conclude that mammoth tusk is at least 80,000 years old. Okay? Does that logic make sense? Could someone please explain it to me? Okay. Moving along, assuming that we do. Same thing for Valine. This is a good check. Sure enough, we get a good split here. And sure enough, terrace 1 falls into the 80,000 year range. Terrace 2 is 120. Okay? So, put that back in our oxygen isotope curve again. What we're looking at, here's our present interglacial. There's the last glacial when most of the mammoths were living that have been dated by radiocarbon. But this guy falls into this minor high sea stand here at 80,000 years old during stage 5, which is part of this complex of high sea stands from the last interglacial. Here's the 120,000 year terrace. That is the one that is the second terrace at Guiranon Canyon. And we're missing this one in the middle, which is often the case in California. But this guy is around 80,000, okay? But that's a relatively high sea stand, right? You remember we said the distance is minimized during glacial periods. So that certainly wouldn't have been the case during this relatively high sea stand of the last interglacial complex. Certainly wouldn't have been the case here, where sea level is actually higher than present. And here it was just a little bit below present. So if it's 80,000 years old with a host sediment, that means that mammoths probably went out there earlier still, like during stage 6, stage 8, stage 10, something like that. Some earlier period when they initially came out. Now that mammoth could have been living out there 80,000 years ago, fallen into the surf zone, left for us to look at 80,000 years later. But the ancestors who swam out had to have come out probably during a glacial period prior to that, evolved down to their small size as they did during the last glacial period. So there we got to be looking at a glacial period. So those are the options. So this is a similar kind of thing, although this is an actual sea level curve. This was derived from sediment records in the Red Sea. And so here's our present interglacial. This is when we had most of our radiocarbon dated mammoths. And because we have both Pygmy mammoths, Mammuthus exilis, and Columbian mammoths out here, we think that Columbian mammoths must have migrated out during stage 2, or the last glacial period. We have both of them. But here, during this particular stage, part of this last interglacial complex, or stage 5, 5.1 is our 80,000 year marine terrace where we found this Pygmy mammoth. So the candidate periods that I think are best for this migration would have been during stage 6. Sea level was quite low then, comparable to what it was during the last glacial, or possibly stage 8. That would have been about 250,000 years ago. Stage 6 would have been about 150,000 years or so ago. Okay? So we're really pushing the antiquity of the mammoth back farther than the 80,000 of the host sediment, but back probably, or realistically, to at least 150,000, possibly, if you've had a few beers, you might claim 250,000 years or so ago. Okay? But in any case, older than that 80,000 years, because it's not likely it could have swum out during an interglacial. Okay? All right, so almost done here. So here's the sequence through time that we can see. And this is how uplift ended up in the title of this talk as well. Marine terraces, you remember we said, are formed by uplift. Okay, there are evidence that uplift is continuing on an island, on the mainland, both of them. And at some point during the early part of the glacial, interglacial time period we call the Pleistocene, we would have had some of the earliest marine terraces forming on the islands out here. These are Channel Islands on this side, California mainland on this side. Same terrace would have formed on the mainland because sea level would have been forming both of them. And then during a glacial period, sea level would have lowered. We would have had uplift going on, uplift going on. During the next glacial period, another marine terrace would have formed during the prior interglacial. Sea level dropped. And then ultimately, through some point in time, we would have reached a period where the uplift would have taken place sufficiently on the islands and on the mainland so that the distance between the two was short enough for mammoths to swim across. So we know now that that probably occurred at least back around 150,000 years or so ago, possibly earlier than that. Okay? And then during the last glacial period, we know they did it again, because that's where a lot of our radiocarbonates come from, both Columbian mammoths and Pygmy mammoths. And it's interesting to speculate. Some of the Pygmy mammoths that date to the last glacial period possibly had ancestors that were Columbian mammoths that came across during the previous glacial period. And then new Columbian mammoths came across during the last glacial period, found all the pygmies out there and said, "My, you guys are short." And then the pygmies would have said, "Well, just wait till you see what there is to eat out here. You're going to get shorter, you're going to die." So that's probably how the progression occurred, or at least that's permitted by the data. Okay? The other possibility is that there was a succession of migrations across, and there was intermixing. There's all possible variations that you could imagine that could occur in a scenario like this. And we don't know that it was 150,000 years ago that this occurred. Possibly it was 250,000 years ago. Maybe for some reason nothing happened 150,000 years ago. We have no way of knowing for sure. Okay? But we know it happened at least one time, at least prior to the last glacial period. Had to have occurred at least once before that. Now, what's interesting is the Channel Islands aren't the only place you find mammoths and other proboscideans on islands. They're all over the place. A lot of the Russian islands, islands in Asia from Japan all the way down into Indonesia, all through the Mediterranean, and the Pribilofs in Alaska as well. The interesting thing about the Wrangel Island mammoths, those guys lived until 2,500 years ago. Those guys almost made it into the present world of fauna that we have. So when the pyramids were around for 1,500 years, we still had Pygmy mammoths on Wrangel Island in Siberia. When Buddha was born, we still have them. So it's interesting. Now, not all of them were mammoths. The ones shown in red were where we had mammoths. Okay? And in places we had mammoths and other proboscideans, like stegodons and so on, which are now extinct. And in other places we had just elephants, or ancient elephants, or stegodons, such as some of the parts of the Mediterranean and the Philippines. Now, is it possible that a lot of these guys could have swum out to those islands as well? Well, some of them you don't need to. Wrangel Island, you can walk out there because the sea ice builds up to the extent that all you got to do is walk across. That's no problem. Same thing true with Sakhalin Island north of Japan in Russia here. There's enough sea ice that develops in the wintertime that you can actually just move across. And in some cases, like the Pribilofs, sea level lowered to the point, like on the Channel Islands, where the mainland was actually connected to those islands. Okay, they didn't have to swim at all, but it had to be during a glacial period when sea level lowered sufficiently. The shelf there is much shallower. But as it turns out, there are a lot of places where you don't have those conditions applying. We know that's the case in the Channel Islands. No land bridges, no ice bridges. Same thing with a lot of the Mediterranean islands, some of the Indonesian islands, Philippines, and the Ryukyu Islands of Japan. They had to get there during lowered sea levels, probably by swimming. And good old Don Johnson speculated about this as well. 2 years after he wrote the Channel Islands Swimming Elephants, he said, well, gee, if this explains how we get mammoths out on the Channel Islands, maybe the same thing occurs on a lot of these other islands as well. And he's probably right. And if, again, the model of the Channel Islands is correct, it could have occurred multiple times on those islands as well, because glacial interglacial cycles occurred and affected these islands as well. pre-last glacial mammoths on all of these islands as well. I'm going to go for these. I think that'll be fun. So at any rate, but studies on the Channel Islands, once again, can have global impact in their import. Something we've been finding again and again. That these islands that we call the Galapagos of California, they have that kind of significance, in my view anyway. And thank you very much.